Alright, welcome back. In this video, we're going to go through the PSLE questions from 2016 to 2022 on energy, specifically energy conversions, forms and conversion. Alright, let's get started. Alright, in this question, it's a 2018 question. Solar panels are placed on the rooftops of some houses to produce electricity during daytime. Now, which energy received by the solar panel is used to produce electricity? There's several clues here. Daytime, alright, solar. Now, of course, solar panel receive light energy. There are two kinds of energy that come from the sun. Alright, solar energy, there are two kinds. One will be light energy. One will be heat energy. Now, the ones that can be converted into electric energy from light, right? In this case here, we use solar panel to convert light energy to electrical energy. So the answer is 1. Okay, next question. Now, diagram shows the moment when a rubber ball hit the ground. After the bounce, the ball reached a lower height than when it started. Now, what was the energy conversion at the moment when the ball hit the ground? As a reminder, if you are not used to watching my videos, I will always recommend that you pause the video first, look at the question, try to answer it before you play the rest of the explanation. Right? Now, rubber is an important thing. Now, if this is a glass ball or metal ball, it's a totally different idea altogether. Now, rubber has certain characteristics, one of which it is elastic. Right? It can be compressed, it can be stretched. That's rubber. Think of rubber band, right? You can compress it, you can stretch it. So when a rubber ball hits the ground, it will be slightly compressed. Alright, so there will be some energy stored in a compressed rubber ball. What is that? That is elastic potential energy. So after that, it will bounce up. But of course, it can't bounce to the same height as before because some of the energy would have been converted into things like sound and heat energy. So at the point when it's at the top before it's released, the potential energy at the highest point is the maximum. Kinetic energy is 0 before the ball is released. Once the ball is released as it travels, the height is now lower, right? Now, what affects GPE? The mass of the ball and the height of the ball. The mass of the ball remains unchanged, but the height now has decreased. So, of course, it has less GPE than before. What did the GPE become? Some of the GPE became kinetic energy. As it goes all the way to the bottom and hit the ground, the kinetic energy goes to 0 once it hit the ground. Alright? No, because it's not moving. So all the energy here is converted mainly into elastic potential energy and some sound and some heat energy. So that's why the answer is number 3. The kinetic energy in the ball converts into elastic potential energy in the compressed ball and plus sound. Boom, sound. Okay, next question. A ball tied to a string was released. It swung and hit the plastic bottle. The bottle fell down. Take a look, step by step. First step, the ball was released. So before it was released, it was here at the starting point. So at the starting point, at the maximum GPE. Then it swung down. As it swung down, the GPE decreases because GPE converts to kinetic energy. So it's more kinetic energy. And then as it swung, it hit the plastic bottle. Biang! It hit the bottle. What happens? Right, the kinetic energy in the ball now converts to kinetic energy in the bottle. Why is there kinetic energy in the bottle? Because it fell. To fall, it must have moved. And because it hit it, there will be some sound energy as well. So the answer for this, potential energy of the ball at first before it was released. Alright, as it swung, it converts to kinetic energy of the ball. When it hit it, it became kinetic energy of the bottle as it fell. Because to fall, it must be moving. Right? It must have been moving. Next. This one is a bit tricky. Now, the diagram shows a toy car moving forward due to the air stored in the balloon. Now, which of the following shows how the energy changes? Again, you must always always notice the type of material used to make an object. Or the object itself, like a balloon. The only balloons you know in your entire life is made of rubber, isn't it? Why rubber? We talked about it before. Rubber is elastic. You can stretch it. If you stretch it, you will store elastic potential energy in the balloon. And this balloon, look at the picture, it is inflated. This is actually an inflated balloon. That means that the balloon is stretched. So once, for example, if the finger was at the nozzle of the straw and the finger is removed, air starts to rush out. Why will air rush out? Because the inflated balloon, the stretched rubber of the balloon, will now start to return to its original shape and size. As it does so, it will push the air inside, and the air inside has nowhere to go but down the straw and out of the straw. Okay, so the first step is there must be potential energy. So potential energy is here, is in the stretched balloon. And then it converts and moves. And this pushes, and the air that comes out pushes against the air that's outside. There's air in the surrounding, remember? It pushes against the air outside and makes the toy car move forward. As it moves forward, this is at the same time, right? As it moves forward, there will be kinetic energy in the car. And as the wheel spins against the ground, it rubs against the ground, and heat energy will be generated between the wheels and the floor. So the answer is 4. This is from the 2021 question. Now this one involves a lot of graph reading. A block of wood slid down a slope after it was released at the top, as shown in diagram 1. The graph shows the amount of different types of energy of the block at point P. Notice at point P it is important. Why? Number 1, point P is above the ground. When the object is above the ground, there is GPE inside. Of course, there's less GPE here than here, but there is some GPE here. So this amount of GPE, right, at this point, at this E level. Now, what is this other form of energy? Remember, here is always maximum GPE before you release it, and KE is 0 KE. So that means that the amount of GPE here, this amount of GPE as from compared to this point, has been converted to kinetic energy. And as it slides against the surface here, it will rub against the surface and generate heat energy between the block and the surface. Now they repeat the experiment with oil applied on the surface of the slope. And look at the question, which graph correctly shows the amount of different types of energy at P? See, at P again. So what is the significance? At the same point, P means at the same height as before. At the same height as before means the amount of GPE must be the same. Since it is the same block that was sliding down. It's the same block of wood that was sliding down. There are two things that affect GPE. Recall, mass affects GPE as well as the height of the object affects GPE. So in this case here, what will be wrong? Here is wrong because the GPE here exceeds the original amount that we saw here at level E. This one is wrong. The GPE here is less. The only two options will be these two. The GPE is at the same level. Now, if there's now with oil applied on the surface, therefore the frictional force between the block and the slope is reduced. If you reduce the frictional force by making it more slippery, when you reduce the frictional force, there will be less heat generated between the block and the surface. So therefore, comparing this amount of heat and these two, this one has less heat than this. And because it reduced the amount of frictional force by applying a lubricant like oil, therefore the block will move faster than before. So the amount of KE should be more than before. Therefore, this is the one with the more kinetic energy. Answer is 3. Next one, a spring is compressed and released at A. So here you compress the spring and you didn't let go. So didn't let go means there are lots of GPE here. KE is 0. Then you let go of the spring. As the spring springs up, it's higher than before, right? It's higher than before. So now the GPE is the highest at this point. And the K is the least because it's still moving up in the parabolic manner. This is called parabolic. This kind of movement trajectory shape is called parabolic. As the least amount of KE here and the most amount of GPE. As it goes all the way down and just before it hits the ground, have not hit the ground, just before. So the height is now very, very minimum. So the GPE is at the minimum. KE now is at the maximum because most of the GPE now has been converted to the kinetic energy of the moving spring. But notice the spring here and the spring here, this is compressed. This is no longer compressed. It has returned to its original shape. So what does it mean? So there is no GPE here. Sorry, there is no elastic potential energy. None, because it's not compressed, it's not stretched. It has returned to its original shape. This was a compressed one in EPE. So here there is some EPE, maximum, or there are some EPE. Here there is none. So I should look for something with no EPE. Here there is no EPE, there's nothing here. There's no EPE here. There's some EPE here, elastic potential energy. This is wrong. This one, there's some EPE, this is wrong. So this is how we narrow down the choices to number 2 or number 4. And then we go back to the other two, GPE and KE. Remember here, minimum GPE, maximum kinetic energy. So comparing these two, how can the GPE and KE be the same? Cannot be. Alright, so there must be the least amount of GPE because it's at the lowest point just before hitting the ground, and the K is the maximum. Therefore, 4 is the answer for this. Alright, next one. Now let's recap some science concept here. Now many energy conversion questions are based on changing height of the objects. Because objects at higher height has more, what is this? Has more gravitational potential energy. And in order to change in height, objects have to move. And the idea of moving means kinetic energy. An object that does not move has no kinetic energy. Now, Peter has a flying bird toy. Okay, so you can see the rod here. Now, of course, science questions are like this. You've got to be able to read not just the words, but the picture. When you read words, you got to understand what the words mean. Same thing for pictures. You got to try your best to understand what the picture means. So you see a plastic wing. This is actually a flap. You can try to shade it for you to see. This is actually a flap. Can you see a flap? That's a part of the wing, and this part is like the bottom part of the wing. Okay, I hope this makes the wing clearer to you. Okay, and this is a rubber band, and you can see that the rubber band is being twisted. Right, when you twist the rubber band, it turns into this kind of shape. And there's a handle for you to turn. Like turn the handle around. Right, as you turn the handle, you twist this. And as you twist this, right, you notice then this rod, the wings will move up and down when the handle is turned. So there are other words here to help you to understand. As you turn this, the wings will move up and down. So when you let go, what happened to the twisted rubber band? It will untwist itself. As it untwists itself, it will spin the handle. As it spins the handle, the wing will move up and down. So Peter turned the handles 50 times and threw the toy into the air. So the toy went up into the air. See? He threw it up into the air. The toy flew from A to B. This part is where he was throwing it. The throw was here. So here, as he threw, once he let go, alright, the wings will start to move because it let go of the handle as well. And it gained some height. And here, the height remained level. See? Level from B to C. Before stopping at D. So notice here the height starts to decrease. It's no longer able to fly level. It couldn't fly up as well. It started to decrease. So fill the boxes with the main forms of energy. The toy is flying from A to B. So here, take note. A to B, what is the main forms of energy? There are several terms here. Main forms, flying. Flying is a kind of movement. Okay, flying is movement. Once you know it's flying, you know there must be one form of energy. So let's go back to this. So what's in the rubber band that was twisted? So rubber band has elastic potential energy. Now I'm sure you're asking, can I just write potential energy without elastic? Can. The word elastic here is optional, but I'm writing it down because I do teach my pupils there are different kinds of potential energy. There's chemical potential energy, which you find in batteries, stored in batteries or stored in food. There are in fossil fuels. There is this other form of potential energy known as gravitational potential energy. It's energy stored in an object when it is at a certain height above the ground. Right? And there's elastic potential energy stored in an object that is either stretched or bent or compressed. So this is energy in the toy in the rubber band. But what about in the toy? Definitely you know that there will be kinetic energy, because it was moving. Okay, as it was moving. And as it was moving, was it above the ground? Was it gaining height? Notice here, certain height above the ground. Here, even higher above the ground. It's from A to B. Yeah? So the height was increasing. What was making the height increase? It must be the spin, the flapping wings that help it to gain in height. So there must be some. It was gaining what energy? Yes, it was gaining the gravitational potential energy. Okay? Gravitational potential energy. Now next, why did the toy flew lower and lower from C to D? Right? So what happened? So it must have, now first understand why it could fly higher, right? Because there was the rubber band that was stretched, there was elastic potential energy stored inside. So as the rubber band unravel and return to its original shape, it helps to spin this and help to flap the wings that allow it to fly higher and higher. Now, can it unravel forever? No, it cannot. What happens when it stops unraveling? What happens when it stops spinning? If it stops spinning, then the toy's wings stop flapping. If the toy stops flapping, the wings stop flapping, then what happens? It can no longer fly up higher. Think about this. Now, this is not an easy question to answer. So to answer this question, let's take a look. Now, at this point in time, alright, as you can imagine, the twisted rubber band is no longer twisted. So first you need to show understanding that the rubber band was no longer twisted. So what? So there was no more elastic potential energy in the stretched rubber band because it's no longer stretched. Right? In the rubber band. So I should not use the word stretched because it's no longer stretched. There was no more elastic potential energy in the rubber band. If there's no more elastic potential energy, what happens? So then there isn't any elastic potential energy that could convert into kinetic energy to flap the wings. Because you need to have flapping wings for it to fly. Right? Plastic wings move up and down. But when it's no longer flapping, right, it could not keep it flying. So gravity pulled it to the ground. I repeat, the rubber band was no longer twisted, so there was no more elastic potential energy in the rubber band that could convert into elastic potential energy to flap the wings to keep it flying. So gravity pulled it to the ground. Peter added another rubber band of the same type to the toy. So now there are two rubber bands. Two rubber bands of the same type means if you twist it 50 times again, you will have increased the elastic potential energy by times 2, right? Because there are two rubber bands. He threw the toy into the air as before. Draw a curved line on diagram 2, which is this diagram, to show the new path of the toy. So if there's more elastic potential energy, that means it can convert to more kinetic energy. That means it can fly higher and therefore gain more gravitational potential energy and can fly further. So any line that's above this and lands further will be correct. Now this kind of question is very easy to overlook. So sometimes some of you even forget to answer this. So do make sure you do it. If I were you, I'll do it in pencil because I do not wish to make mistakes. If I do, I can remove it. Now for the purpose of the video, to be clearer to you, I'm using my pen. So starting point is still at point A. So now my new path, you'll fly higher and further. And you'll stay level for a longer time before it comes down. Okay, and hits the ground. So this will be my new path. You fly Y here because it's higher than before. And my flat part here is also longer than the previous one. And where it lands is further from the previous. And that is my answer for this. Next one is a 2019 question. Now, Zhiming set up the apparatus below to investigate how his toy car can move on its own. Oh, move on its own along the plastic track down from A, which is here, to B, from here A to B, and then up to C before leaving at D. Now, C is at a fixed height above B. Fixed height, remember? When we talk about height, this idea, many energy conversion questions are based on changing height of objects. Objects at a higher height has more gravitational potential energy, and in order to change in height, objects have to move, which need kinetic energy. So let's understand this. So the toy car is also at a certain height above the ground. See, at a certain height above the ground. And is this height the same as the height of point C? Let's see. I use my ruler and just take a look. Yeah, it's at the same height. As you can see, same height. Now, here there will be maximum GPE and 0 KE. As it travels down, the GPE will convert into KE. But as the wheels of the car rubs against the plastic track, there will be heat energy. There could be also some sound energy. So by the time it reaches here, you have the maximum KE, but this maximum KE will not be as much as the maximum GPE because some of the GPE has converted into heat and sound. Let me draw this way. If this is the GPE at first, let's call this maximum GPE. As it travels down, it will convert into KE, but some will convert into heat energy, some convert into sound energy. So if I further help you to imagine, let's say there are 10 units of GPE at first. Maybe 8 converts to KE. 8 of these convert to KE. And 1 unit converts to heat, 1 unit converts to sound energy. Total is still 10, right? 8 plus 1 plus 1. But now there's less of this. And then furthermore, as the car that is here now tries to move up, it continues to rub against this surface. So as the KE of the car here is converted to GPE of the car, here is whereby the KE now converts to GPE. But as it moves along the track, there will still be sound. There will still be heat energy. Get it? Therefore, by the time it reaches here, for example, if 1 unit changes to sound, 1 unit changes to heat, and there is 6 units of GPE, how can it get back to the same height as before? It cannot, maybe up to here, then it starts to swing backwards. So this explains basically why Zhiming's car could not reach C. It's a 1-mark question, so explanation doesn't have to be too difficult. And the answer is basically this, right? There just wasn't enough kinetic energy. Remember I said kinetic energy here is less than the GPE at first. So there wasn't enough kinetic energy of the car at B. Be very clear to your marker what you're talking about. Not enough KE to do what? Not enough kinetic energy to move the car, because kinetic energy is energy that represents movement of an object. So there is not enough kinetic energy to move the car all the way to C. Just not enough. Right? That's enough for 1 mark. Now, without using different apparatus and additional material. This is an important thing. This is what we call a conditional statement. So you're asked to repeat the experiment and change some things in the setup such that the car can reach C. But you cannot use different apparatus. You must use the same clamp, the same stand, the same joint, the same flexible plastic track, the same car. You cannot change them. And you cannot add additional materials. So basically, use the same thing. So let's go back again. We need to have an idea. We are going to achieve it to reach C. So therefore, the car must move faster than before. It needs to have more KE, right? Because here, remember, there wasn't enough KE. Sorry, not enough kinetic energy. Exam time, you cannot write KE as answer. Cannot. Sometimes I use KE in my verbal explanation to you or in my notes to you here, so to reduce the amount of writing you need. But when you write down your answer, you cannot use KE. We do not know what is KE. Okay, you've got to tell us it means kinetic energy. So if it couldn't reach C at first because there was not enough kinetic energy, so you need to give it more kinetic energy. Makes sense, right? If you only have 10 cents, not enough money to buy a 50 cents chicken nugget, you need more cents. You need 40 more cents. So how can we give the car more kinetic energy? Well, several ways. Think about it. One way is to raise the joint higher. What joint? This is a joint. And it already told us so kindly, it's an adjustable joint. So I can raise it higher. But is it enough to get me 1 mark? Because 2 marks, right? So 1 mark here and 1 mark here. Not enough because I only suggested a way. I suggested one way, raise the joint higher, but I failed to do something. I failed to explain how does raising the joint higher helps. Raise the joint higher so the car starts at a higher position. So once the joint is higher, the car will be higher. It's a flexible track, right? It's not a fixed track, right? It's higher. When it's higher, so there is more. So the car starts at a higher position with more gravitational potential energy. To convert into kinetic energy. Basically, we want to have more kinetic energy. Okay? So I need these two parts, the suggest a way, and the second part, explain my answer to get 1 mark for this. Now, what's one more way? So I suggest we can push the toy car hard. Now, I'm sure you all understand the idea of release. Release is this, right? If it's a toy car, release is this, just let go. Release means let go. So I'm not pushing the toy car if I'm just releasing it. Same thing when Zhiming released the toy car, Zhiming didn't push the toy car. So all the energy that the toy car has here is dependent on its position above the ground. So all the energy it has here is just the GPE. But by pushing the toy car hard, what am I doing? Now, of course, remember, this is just suggest a way. I have not explained yet. So how do I explain the purpose behind pushing the toy car? The idea of pushing is an action. Pushing is an action, right? It's a movement. So pushing the toy car hard gives the car more kinetic energy from the start. Remember, all we want is to have more kinetic energy. Because at first, why it couldn't reach point C? Because there wasn't enough kinetic energy by the time it reaches point B. So I need to give it more kinetic energy. Next one, state the main forms of energy that the car will have at C. Now, the questions ask for stating. So there's no need to explain. Okay, no need. So when the car is at point C, so I draw the wheels of the car. Now it's upside down. The car is here. Point C, and these are the wheels. So what energy does it have there? And here they put down very tricky. They put a bracket with S. So it can be, you can think of it as one answer or more than one answer. Now, if you have only written down the answer, gravitational potential energy, or just simply potential energy, you would have gotten half a mark. Why? Because the car is still moving there. Remember, it is still moving. Why? Because the car is supposed to move up to C before leaving at D. So the car is moving this way up and continue to move until it leaves the track at point D. So therefore here, it must have one more. And kinetic energy. So there are two forms of energy here, half mark for each. Now let's revise what chemical potential energy means. potential energy means stored energy. So it can be stored in, as I mentioned earlier on, it can be stored in things like dry cell or a battery. It can be stored in food. It can be stored in fuel. So this is like a oil drum. We put petroleum inside or petrol inside. Now, Peter has a toy train that runs on batteries. This is a 2018 question. He placed plates of food on the train as shown below. So it's you go to Sake Sushi or some restaurant, they will have something like this, a conveyor belt. Of course, this is a toy. Now, and the toy runs on battery. So the battery here has stored energy. Now, when he switched on the toy train, it moved along the track, filling the boxes below to show the energy conversion as the train is moving. Remember, moving means there is KE. So what is in the battery? One answer only, potential energy. And if you want to, you can definitely write chemical potential energy, although the word chemical is not necessary. So what energy is converted to? You convert to electrical energy. Not electricity, be very careful, electrical energy. And this electrical energy will spin the motor inside the wheels of the toy train and to make it move. So as the train moves, the train will have kinetic energy. And as the train moves along the track, the wheels are moving. Here, there are two possible energy you can write. You can either write down sound energy. As you move, they will create sound. Or you can write heat energy. This is a minor one. The main forms are here. Now, Peter did not change the batteries. Did not. So why did the train move faster as the food was removed? It's like you carrying a backpack full of books versus you carrying the same backpack with 0 books and you are running on the track. In which situation can you run faster? When you're carrying lots of books or carrying 0 books? Of course, when you're carrying 0 books. Why? Think about it. And this is how you can explain it. Right? Think about the example I mentioned earlier on with you carrying a backpack. If you're carrying a heavy backpack, you need to convert your energy to make sure you can carry that bag. Heavy bag with lots of mass. But if now your backpack has nothing inside, the mass of your bag has gone down to the minimum. So you can convert more of your chemical potential energy in you to your kinetic energy to make you run. Similarly, as food was removed, the mass of the train decreases. So more of the electrical energy here can be converted to more kinetic energy, because move faster means that there's more kinetic energy. Next, Peter placed a wooden block under the track at point H. Now I know. Okay, I refer you back to this again. Energy conversion question often got to do with changing height of objects. An object at a higher height has more gravitational potential energy, and in order to change for that to have a change in height, objects have to move, which involve kinetic energy. So you see, by putting a block here, now the train will move to a higher height. See, there's a height now above the table. This is a table. So explain why the toy train moves more slowly. More slowly now means less kinetic energy. Earlier on was move faster. Move faster means more kinetic energy. So why is there now less kinetic energy as it moves from G to H? G to H. G to H. So what did some of the energy went to be converted into? So before that, this is the after situation. This is the before situation. Before situation, when the train was at point G, this is a train, okay, at point G is at this height. When the train moves to point H, the height did not change. height did not change. So that in this case, there was no change in GPE, right? No change in GPE. The mass of the train did not change from G to H. From here to here, the kids can't reach out to get the food, right? So there's no change in mass of the train as it moves from these 2 points. There's also no change in the height, and 2 things affect GPE, height and mass. So here there's no change in GPE. But here there's a difference. Now at this point G, here, the point H. Now here has less GPE, here there's more GPE. What energy was converted into GPE? Let's take a look. Which one? It is the KE. I revert you back to this again. In order to change in height, objects have to move, which need kinetic energy. So therefore, why the train moves more slowly? Try to answer this. So I'll explain it in this way to you. Some kinetic energy of the train, what happened? Was converted into gravitational potential energy as it goes up. Alright? What makes it goes up? KE makes it goes up to more GPE. So some kinetic energy of the train was converted into gravitational potential energy. So with less kinetic energy, the train moved slower. With less kinetic energy, the train moves slower. Right? So this explains why the train moves slower. There was less KE, basically. Less KE in the train. And why was it less KE in the train? Because some of the KE was converted into gravitational potential energy. Okay, again, another train question, another change in height question. So I will again refer you back to this. This set of notes here. Many energy conversion questions are based on changing the height of objects. Objects at a higher height has more gravitational potential energy, and in order to change in height, objects have to move, which need kinetic energy. So you will see these ideas keep repeating itself in many circumstances. So let's try to answer this. Why are wheels such a wonderful invention? Wheels allow us to move objects of large mass using less force by reducing the frictional force between the wheels and the ground. Okay, wheels allow us to move objects of large masses using less force by reducing the frictional force between the wheels and the ground. So that's just an idea for you to bear in mind. Now let's try question 10. Now, Aisha tied a mass to an electric toy train. There's a mass here, tied with a string to a toy train. As shown in diagram 1, this is diagram 1, the one above. The train moved slowly. So it was moving, so there is some KE from A to B. Next, I shall link a wagon. What's a wagon? This is a wagon. It's like a little carrier thing with wheels. So you link a wagon to the train. And when she placed the same mass on the wagon, the train moved faster. Faster means more KE. Same train, same mass, except now there's a wagon with wheels. Now I understand why I ask you about this and teach you this. Wheels let us move objects of large mass using less force by reducing the frictional force between the wheels and the ground. It's like if you were to be seated on a classroom chair with legs, that kind of chair, just the 4 legs, and you sit down on this kind of chair, it's very hard to move you or move a large-sized person. Let's say I'm a large-sized person. If I sit on this, you want to drag me across a classroom, it's difficult. But what if this chair now is special? There are wheels at the bottom of the chair, like a wheelchair, or there are just wheels. Now you can even use a little pinky and just drag across the back of the seat of the chair, and you can most likely pull or push me just using your pinky. Because the wheels help you to move objects of large mass using less force. by reducing the frictional force between the wheels and the ground. If there's less frictional force between the wheels and the ground, of course you don't need to use so much energy as well to move something. So give a reason why the train moves faster when pulling the mass on the wagon. So by comparing these two, you will notice the only difference between these two, the only difference is the wagon. And the wagon has a thing called wheels. So why did the train move faster when pulling the mass on the wagon? The wheels on the wagon helped to do what? Reduce what? Reduce frictional force. Between what? The wheels and the ground. If without the wheels, this mass will have to be dragged across the track. Okay, so I should use the word track instead of ground, because the word track is used in the question. So let's keep to the same words being used. Track. So now we reduce the frictional force between the wheels and the track. When there's less frictional force, of course, you move faster. Okay, moving faster means you must add lubricant or put something on wheels. The train moved from A to B, but moved slowly. Move up the slope slowly. Explain why the train moved up the slope slowly. I think we just learned this just now, remember? Now, up here, there is now increase in the GPE. Increase in GPE. Remember the earlier answer that we learned? Some kinetic energy of the train was converted into gravitational potential energy. So with less kinetic energy of the train moves slower. So same thing here. Why did the train move up the slope slowly? Because I use the same answer. Some of the kinetic energy of the train. What happened to some of the kinetic energy of the train? Was converted into what? Into gravitational potential energy. And with less kinetic energy, the train moved slower. Ta-da! Okay, simple. Another 1, 2, 3, 4, 5 pages. Let's keep it up. And let's think, what happens when you apply a force on a plastic ruler? What happened? The ruler bends. Now remember, weight is a force. So the weight of the wagon on the slope exerts a downward force on the plastic ring. Okay, this is linked to this part. And this force, known as what kind of force? Downward force, weight, known as gravitational force, will, remember, it's a plastic ring. It will bend the ring. I'll come back to this part again after looking through the question with you. Now the train and the wagon were linked by plastic rings as shown in diagram 3. Diagram 3 is here, this is diagram 3. These are the two plastic rings. This one, plastic ring. Notice there's a small opening, a small gap, so you can kind of force these things through. The plastic ring, and it's here, it connects these two together. Okay, connects the wagon to the train, and this part means to zoom into this part of the picture. Now, when the wagon was on the slope, up on the slope here, when the wagon was on the slope, it broke loose from the train and rolled downwards like this. It broke loose and rolled down. Notice here, it opened wider. This gap here was wider compared to when it was here. Almost no, you can't see any gap. It broke loose from the train and rolled downwards as shown in diagram 4. The plastic rings used for linking the wagon to the train were not broken. Let's exert a force and let go of the force. It returns to its original shape. That's elastic spring force, right? But I didn't break my ruler. I just bent it and it returns to its original shape after I stopped bending it. When I apply a force, I bend it. When I let go, when the force is removed, it returns to its original shape. So now, using that idea, explain why the wagon broke loose from the train on the slope without breaking the plastic ring. Go back to the idea of what happens when you apply a force on the plastic ring. The plastic ring will bend. That's the first thing. And why is the force here? It's on the slope, so there's gravitational force. There are 2 marks here, bear in mind, so you need to give 2 points. First thing, explain why did the ring bend. Right, this is how I would ask you to explain this. So gravitational force acted on the plastic ring, bent it and forced it open wide enough to slip through the ring of the train. You see, I use the words here. This ring here is this ring I'm going to highlight in this highlighted orange color. This is the ring of the train. Right, this is the ring of the train. So by forcing this opening, open it wide enough for it to slip through the ring of the train. At first, it didn't slip through because the opening was narrower than the ring of the train. For it to slip through, it got to be, see, I cannot slip through, for example, cannot slip through. Unless this opening now becomes wider, then it can slip through. Right, when it's narrow, it cannot slip through. So let's go back to the answer one more time. Gravitational force acted on the plastic ring, bent it and forced it open wide enough to slip through the ring of the train. Full stop. Now, John wanted to compare how fast a wooden block can move on different planks using the setup below. He released the block, measured the distance moved by the block down the plank and the time taken. So again, height. When you see height, think of GPE. Alright, because the higher an object is placed, the more gravitational potential energy it has. A shorter plank made of the same material, R, was placed at the same height. So let me just draw it out here for you to see. So I'm going to extend out this. I'm going to put down here same height, same height H, okay? This is height H. Same height, so I'm going to draw in red here. Same height. So I use another block and I put it here. And they use a shorter plank now. This plank, if I measure my ruler, is about 4.8 centimeters. So a shorter one, let's make it just 2.5. Okay, 2.5 centimeters using my ruler, roughly. Everything else I try to keep it the same as the previous diagram. Okay, and I put the shorter plank, okay, this is shorter plank, same material R, placed at the same height, and now I put the same wooden block here. Same wooden block. Now, will the block take a shorter, longer, or same time to reach the bottom of the plank? This first part asks you for a claim. Okay, so what is your claim? And your claim is important. There's no marks given for the claim. The claim is important because the claim determines if the marker will carry on to read your answer. So think about the claim. To answer this, alright, and we are told to explain the answer in terms of energy changes, you got to know how the energy conversion happens. So there is GPE in the block. And since it is the same block at the same height, so the amount of GPE in the block is the same, whether it is in this position here or here over the shorter plank. As the block is released, it will slide down the plastic plank, whether it's this longer plank or the shorter plank, and you convert to kinetic energy. And as you know, as it rubs against the surface, there will be some heat energy generated. Now, which surface would there be more heat energy generated. Of course, you rub across a more surface, you have more heat energy. You rub across less surface, there'll be less heat energy. So imagine here if there's 10 units of gravitational potential energy and you rub across a longer surface, a shorter surface, you only convert to, let's say, 1 unit of heat energy, then there's 9 units of kinetic energy in this case. Hooray, right? Quite fast. But in this case here, you have 10 units of your GPE, you convert into longer surface, twice as long as this, for example, so you convert to 2 units of heat energy. Now, and the total amount of energy is the same. So how much of the kinetic energy is left? 8 units of kinetic energy. So which one is slower? Of course, less one is slower. This is for this case. This for this case. So the idea is, when you move across a shorter surface, less heat energy is converted, so there will be more kinetic energy. So claim shorter time. Why is a shorter time taken? Alright, evidence is a shorter Planck means the wooden block travels over a shorter distance. So what if we travel across a shorter distance? Alright, so less of the kinetic energy converts to heat energy. Less of it converts to heat energy. Understand? So here actually, I think I make a mistake here. So if I follow this, alright, it should be less, not kinetic energy, but less potential energy. Less potential energy of the block converts to heat energy, and more converts to kinetic energy. That's why it is faster. If it's faster, it takes a shorter time. So shorter time, why? A shorter Planck means the wooden block travels across a shorter distance, so less potential energy of the block converts to heat energy, and more converts to more potential energy converts to kinetic energy. So more potential converts to more kinetic energy faster. Not in this case. This case is more converts to heat energy, so less kinetic energy. Now, John's result for Planck R as shown below. Okay. Distance traveled 80 cm. At first was 0. After 2 seconds, it reaches 80 cm. After 2 seconds. Now, John repeated the experiment with a wooden plank of the same length. The wooden block moved down the plank more slowly. Now, notice the material changed. This was a plastic plank at first, and then this one changes to a wooden plank. And once you change the material, you will change the surface of the material of the plank, and therefore you will change the amount of frictional force between the wooden block and the surface. Once you change the material, the frictional force will change. If the frictional force changes, then the speed at which the object moves will change too. And John noticed that the wooden block moves down the plank more slowly on the wooden plank. If it moves more slowly, it means it will take more time, right? It moves more slowly, it takes more time to reach the bottom of the plank. So state which graph shows the correct result. More time. Here is at 2 seconds. Remember, 2 seconds, it reaches 80 cm on the plastic surface, plank R. So here, if it's more, it must be here. So this is maybe 2.4 seconds, no? Much longer than before or something. My decimal is probably wrong, pardon me. So this is like 2 point something seconds. 2, 4, 6, 8, yeah, correct. Now, so it will be graph M. Now, besides the height H, okay, and the length of the plank, what are 2 other variables that John must keep constant for the comparison? Now, in this case here, we must first know what is he comparing. 2 different materials, so you're comparing the frictional force, right? So anything that will affect the speed will be the case. So what are the factors that he must keep constant? Okay, so I redraw this here, right? So this question says, beside the height h and the length of the plank, state two other variables that John must keep constant for the comparison. So the only change variable is the material of the plank, alright, is the only change variable. So I use two different colors to represent it. So what is, and h is kept constant already, as mentioned, h is constant. Length of the plank is kept constant. So what else must be the same? Clearly, the wooden block must be the same. So the same wooden block should be used. So by using the words same wooden block, I don't have to go into the shape of the wooden block is the same. I don't have to go into the size of the wooden block is the same. I don't have to go into the mass of the wooden block is the same. By just saying the same wooden block should be used, I cover all these things about mass, shape, size, color, whatever you want to talk about. Same wooden block. Secondly, it is the way the block was released. If I had pushed it, alright, or just let go, releasing, I'll get different results. Right? To be fair, I must release them the same way. Just let go. So I'm not adding additional force to the wooden block as it travels. So I'm not making it move faster or slower by pushing it. So these are the two other variables that John must keep constant for the comparison to be a fair one. Okay, just a couple more questions. Now, Terence drilled a small hole at the bottom of a pail and hung it above a plate. He filled the pail with water, right, there's a missing L, and let the water drip from the hole onto the plate as shown. A sound sensor recorded the sound made by the water droplets. Let me remind you one more time of this thing. Energy conversion questions are based, many of them are based on changing height of objects. Objects at a higher height has more gravitational potential energy, and in order to change in height, objects have to move, which need kinetic energy. This idea is often tested. So you see, height above a surface. Already, once you see this height, you know it's about something about gravitational potential energy. And the droplets are moving, so there's kinetic energy. A sound sensor, there's conversion to sound energy. So as every time the droplets of water hits the plate, you notice there will be sound, like drip, bloop, 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 bloop. So all these peaks shows the times, show the instances when the water droplets hit the plate. Now, state the number of water droplets that fell on the plate in the first 30 seconds. First 30 seconds is up to here. This is 30. So remember, the peak represents the number of times the droplet hits the plate. So the answer is 3. Now, why the sound level is not 0 between 10 seconds and 15 seconds? Now, between 10 and 15, there was nothing hitting the plate. But why was there no sound? Now, even in the quietest of the night, you still hear some sound. I mean, the buzzing of your lamp, or the turning of your fan, or the air conditioning unit, or a dog barking in the neighborhood, or cat meowing somewhere. You always hear some sounds. Those are ambient sounds. Ambient means, the word ambient means surrounding sounds. Right? There will be, on Earth here, unless you're locking yourself in a very secure room with nothing inside, absolutely nothing, you still hear something. You can still hear your breathing. So why is it not at 0? Because there will always be some background noise. There will always be some background noise. And this background noise is what I call ambient sound. Okay, background noise, naturally. Now, using the same apparatus, so no change, is still the pail, still the plate, still the sound sensor, right? Still the same pail of the hole. Using the same apparatus, suggest two changes to increase the maximum sound. So, recorded by the sound sensor. Let's understand the energy conversion here first. So there was some sound, right? Energy. To get the sound energy, there must be some kinetic energy of the droplet hitting the plate. To get this, there must be some GPE at first. GPE of the water in the pail that hit it. So I need to have more sound and the drop of water must move faster. More kinetic energy. To have more kinetic energy, there is more GPE. You see more of this compared to more of this. How do I get more GPE? Now some of you will talk about adding more water, but no point because the water leaves. If you add more water, let's say I fill up this pipe with water, it doesn't help because the water leaves it at this height. If this height here remains unchanged, if I put a lot of water, it's still at this height when the drop of water leaves and hits. So this drop of water will travel the same height. And if the drop of water didn't change in size, so the mass is the same, and the height is the same, GP will be the same, K will be the same, and the amount of sound recorded will also be the same. See, ambient sound, right? Now, so what can we do to increase the GPE? So there's more KE, so there's more sound. Think about this. So go back to basic. What affects GPE? Two things, height and mass. So how can I change the height of the water droplets? Very simple. I raise the pail higher. I'm using the same apparatus, right? I just need to raise it higher. So first change. Must we explain? Let's see. Suggest two changes to increase the sound level. They didn't say explain. So they didn't explain. Thank you very much, examiners. No need to explain. I just tell you what are the two changes I need to make. So the first change I'll make is raise the pail to a higher position. And by saying that, I'll get my 1 mark. So I'm trying to adjust this one. So once I raise it higher, I have more GPE, more KE, more sound. Next thing I can do is increase the mass of the water droplet. In other words, I need a bigger water droplet. What can I do to get a bigger water droplet? I need a bigger hole. The hole is bigger, the water droplet that come out will be bigger, and therefore the water droplet has more mass, more GPE, more KE, more sound. So number 2, increase the size of the hole, okay, in the pail. Now, if I'm asked to explain, I can explain. But since I'm not asked to, hey, let's not waste time. Let's go and focus on other questions in the exam. So be very clear what you're asked to do. So like the earlier question, there was one question here that asked you for 2 suggestions like this. Suggest 2 different ways and explain. To get these 2 marks, it was harder. Harder not because it was difficult scientifically. It's harder because you must do more work. You need to suggest and explain. In this case here, to get 2 marks, thank you so much. I just need to suggest, no need to explain. So be very clear what you are required to do, what you're required to write, so you just give enough. Next thing about energy conversion question. There are also many energy conversion questions that involve electromagnets. The electromagnets will oftentimes make a magnetic rod, a magnetic material or rod or bar move, KE, to hit something and make a sound. And your knowledge of electrical circuits will be tested as well. So next 2 questions here will be about this kind of question. Last 2. Hanging there. You first can take a break, pause the video, have a break before you come back. Kumar set up the apparatus as shown. A, B, and CD are identical iron rods and are fixed in place. Let's see. A, B, C, D, they are fixed in place. Fixed means cannot move. PQ is an iron bar with a hammer at one end and rests on the fixed metal nail. So PQ, I'm going to color PQ red. PQ it rests on an iron. What does rest means? Like my pen is resting on my finger, but it's not fixed to my finger. It's just resting on my finger. Okay, that's called resting. Okay, so idea of resting is just lay on top. That's it. So let's say I move the angle this way. If it's resting, can I move up, down, up, down? Can. So it's not fixed. This is fixed. Now I can move up or down. When he closed the switch, the hammer struck the bell repeatedly, to give a continuous ding, 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 ding sound. Explain how the sound was produced. 2 marks. Now, very often you've got to give step by step to explain. That's why you give you 1, 2, 3, 4, 5 lines, because you've got to explain how this thing happens step by step. Starting from he closed the switch. Okay, let's understand the diagram. Read the diagram. So the switch is open now. Open switch means now this circuit is open. If it's open, means current cannot flow through. If current cannot flow through, then of course whatever is supposed to work won't work. Once the switch is closed, current can flow through. So step 1, I'll put 1 here to show the steps. So step 1, as the switch closed, current flows through the circuit. This is common sense, and this will give you half a mark. As the switch closed, here, let me close the switch with this. As the switch closed, current flows through the circuit. So let's trace it with my highlighter. Current flows through. This is a plus, this is a minus. This is a long one is a plus, one is a minus. The current flows through, the circuit flows. And these 2 rods are iron rods. And iron is a magnetic material. So it flows through, flows through, flows through, flows through. As it flows through, and this you notice that it is coiled around iron rods. So these 2 are effectively electromagnets. Right, it flows through here. It's a fixed support, and the wire is here, and it touches this part here. Okay, and this is PQ is also iron, right? Iron is not only a magnetic material, it's also a conductor of electricity. Let's make sure you are very clear. It is a magnetic material. It is also a conductor of electricity. This part here is your electromagnet. This part here is simply the current flows. See, current flows. It's a closed circuit, current can flow. So what happens when these become magnetized? And this is a magnetic material. It will then attract and pull this up. And what happens when this PQ moves up? This is like a spring that can be compressed. When it pulls this up, what happens? Sorry, it pulls it up this way, because this is like a hinge, fixed support. So imagine my red pen now is the PQ. It pulls it up. You can see now the hammer hits this, ding, pull up and hits. And once it pulls it up, I'm going to just erase my PQ and my hammer. Okay, it's going to go up and strike this. Once it goes up, notice that now PQ is no longer touching the fixed metal rod, fixed metal nail. Once it's not touching, this is an open circuit. It's a gap. Open means current cannot flow. Once current cannot flow, what happens to the electromagnet? It will stop working. Then there's no more attraction, there's no more magnetic force. Then this PQ will come back down again. And once it comes back down again, you can see now, comes back down again. Now it will touch again. A current can flow again. Then it will attract again, become electromagnetic. Attract again, goes up, ding, hit again. Once it leaves, this is no longer touching. Then the circuit is broken. It's a gap. Current cannot flow. this electromagnet will not work, and it will fall back again by gravity. Okay, so step by step, make sure your examiner understands. So as the switch closed, current flows through the circuit and magnetizes rods A, B, and CD. So first talk about these two becoming an electromagnet. It magnetizes these two. So what happens when it magnetizes these two? Well, after attracting PQ up, and what happens? You attract rod PQ up and cause the hammer here to hit the bell, causing a ding sound. Hey, I'm almost done. I got 1/2 mark explaining current flowing, causing these two rods to become an electromagnet, attract PQ up to hit this. But the problem is I only talk about the first ding. How about the rest? What caused the rest of the sound? Well, I'll explain like this. When PQ, this rod, leaves the nail, which is here, the circuit is open. So what happened? And the electromagnet stops working. So what happened? So PQ falls back to the nail, and step 1 here repeats. Repeats means switch closes, current flows through the circuit, magnetizes rods A, B, and CD, attracts rod PQ up and causes a hammer to hit the bell, causing a ding sound. And then PQ leaves the nail, circuit is open, and electromagnet stops working, so PQ falls back to the nail, and step 1 repeats. That's why I have the ding, ding, ding sound repeatedly. So this is how I would answer this and get all my 4 half mark, giving me 2 marks. It's tedious, it's not difficult, but it's tedious. You just need to be as clear as possible. Like I told my students, explaining questions like this is like trying to teach a primary 1 child how to cook Maggi mee. You got to give the child step-by-step instruction. Pour water into the pot. Pour half a cup of water. Heat it to boiling. Then open the Maggi mee, put the Maggi inside. Cook until the noodle is soggy. And then, step by step, how long should you cook? What's the temperature? Must be as clear as possible. Next, Kumar replaced the spring with a stronger spring of the same size. This spring, same size. When he closed the switch, the hammer struck the bell repeatedly. State 1 effect on the sound produced. Explain your answer. 2 marks again. So how would the spring here affect the movement? All right, the amount of sound. So you see now it's a stronger spring. A stronger spring will mean that there will be more elastic spring force. Elastic spring force. Elastic spring force. Meaning it takes more force to compress it. It takes more force to compress it. So in other words, now for this to move up, it's a bit harder than before because now this guy is pushing, not so easy to compress a stronger spring. It's not easy to compress a stronger spring, which means this hammer will hit this. This whole thing will still move up and be attracted to the electromagnet, but it will not move up as fast as before. If it's not as fast as before, the KE of the hammer hitting this will be less than before. So the sound will be softer. So here I must give 2 answers. First, state the effect on the sound produced, and then I must explain. So first I'll talk about the sound produced will be softer. Okay, and this is the effect part. Now I need to explain my answer to get the second part of the mark. How should I explain it? This is how I advise you to answer this. So the stronger spring will slow down the movement of rod PQ. Slowing down means the hammer will strike the bell with less kinetic energy, so resulting in less sound energy. Okay, so 1 mark for the effect, 1 mark for the explanation, which is the science behind this. Next, state the effect on the sound produced if the fixed metal nail is replaced with a wooden rod of the same size and shape, and explain. So I need to state the effect and explain. Let's see. If the fixed metal nail here is replaced with a wooden rod. Now, very importantly, metal is a conductor of electricity. Now, if I replace this fixed metal nail with a piece of wood, current cannot flow through anymore. If current cannot flow through, I can close the switch, but it will still be an open circuit because this part here, there is no current flowing through. If no current can flow through, these two will not be electromagnets. If they are not electromagnets, PQ will not be attracted. There will be no magnetic force to attract the PQ. If there's no magnetic force to attract PQ, the hammer will not hit the bell, so there is no sound. So what is the effect on the sound produced? There will be no sound produced at all. Why? Very simple. This is the first answer, state the effect. Now the second part, must not forget to answer the second part. Explain why. Wood is not a conductor of electricity. Simple, right? It's not a conductor of electricity. So, current will not flow and the electromagnet will not work. Alright, let's go to the last question. Now, Sammy set up a doorbell as shown. The iron is a conductor of electricity. Iron is also a magnetic material. The iron cylinder, where is it? Iron cylinder. Whenever I see wire coiled around a magnetic material, it tells me this thing here is my electromagnet. Okay, my electromagnet. The iron rod can swing about point P. So what does it mean, can swing about point P? Point P is like a pivot. So as a pivot, it's like if I were to put this pencil here, it can swing about my fingers here. Right? My fingers hold this part in place. This part is fixed, but this part is not fixed. This part can move, but this part cannot move. Okay, that's the idea of it's fixed here. It swings about point P. That's the idea. So this is like my point P. Okay, swings about here. If it's like that, it swings like this. This point P, it swings like this. So this is like this. My pencil is like the iron rod, swinging like this. So the spring, a spring is fixed to the iron rod. This is fixed. Fixed means this part is fixed, this part is fixed. So spring can be compressed or can be stretched. And it's iron again. Iron means it's a conductor of electricity. It's also a magnetic material. So I can imagine when you turn on the switch, current flows. This is plus, this is minus, plus, this is minus. Current flow through the wires and turn this into an electromagnet, which will then exert a magnetic force on the metal rod, which will then swing this rod here, such that it will hit the bell. See, this part here will move here and hit the bell. And how many times will it hit it? Just once. Dong sound. It's unlike the previous one, because here the circuit is not broken. Right? It is just turned on. The current just keep on flowing continuously. So the electromagnet keeps working continuously. So there's continuous magnetic force here. Therefore, it will just stay in this position. Dong. When you close the switch, the iron rod hit the bell to produce a ding sound. But then when he opened the switch, so he opens it. Once he opens it, there's a gap. Current cannot flow. Then the electromagnet stops working. It stops working. There's no magnetic force. No magnetic force. Then, because if this is here, it means the spring has stretched, right? You stretch the spring. Once there's no magnetic force to keep this end of the rod P here, the spring will pull will pull P back. And the top part here will now hit plate R to produce a tong sound. Explain how the ting sound is produced when you close the switch. So first part, explain the ting part. So let's look at the diagram and try to understand how to explain this. This is how I think you can answer this. Now, of course, if you can give a shorter answer, please write in the comment section below and tell me how will you answer in the shorter form. Now, for me, this is the most concise way I can answer it. Maybe I'm a bit long-winded, that's why I missed the long. When the switch is closed, what happens when Sammy closes the switch? When the switch is closed, so I missed a C here. When the switch is closed, current flows through the circuit. And what happens when current flows through the circuit? The iron cylinder becomes an electromagnet, right? Iron cylinder becomes electromagnet. What happens to electromagnet? It exerts a magnetic force on the iron rod. And what happens when it exerts a magnetic force on the iron rod? It will attract it and cause the top to hit the bell. The top part to hit the bell. Okay? And that's why there's a ding sound. Suggest two changes to the setup to produce a louder ding sound. So let's go back to the energy conversion. Whenever you're asked to do things like louder sound, faster, we always go back to the energy conversion. Remember the earlier questions? Go back to understand the energy conversions first, then you know what needs to be done. So likewise here, what is the energy conversion here? So there is some energy stored here. So this is your chemical potential energy in the battery. There are two batteries, sorry, so plural. This is converted to electrical energy in the wires, which it converts into electrical energy in the wires, turn to electromagnet already, right? And then this one will create, there'll be a magnetic force. Now here, of course, there's no more converters, there's no magnetic energy, it's just here. Now, in order to have a stronger electromagnet, I must have more electrical energy. If I have only like one battery, then of course the electromagnet will be weaker. So what are the two changes to produce a louder ding sound? So first one I can talk about, and I didn't say I cannot change anything, right? So I can change. I can add more batteries. And must I explain? No need. Suggest changes. Add more batteries. Second one. Okay, what else can I do? I want a louder sound, so I need more electrical energy. I mentioned that already. What else? Now let's understand about magnetic force. Magnetic force is a force that acts at a distance. So the further a magnet is from an object, the weaker is the magnetic force. The nearer the electromagnet is to the object, to the magnetic object, the stronger is the magnetic force. So if I want this ding sound to be louder, I will need it to hit it with a harder force. Harder force would mean I need to attract it with more force. Okay, if I hit this very lightly, I hit loud, very hard. Different, right? So if I can move the electromagnet nearer to the end of the iron rod, then the magnetic force will be stronger. That's one way. Or I can also change the spring to a weaker spring. If the spring is weaker, it will not slow down this rod as much as if I use the earlier spring, because then there's less elastic spring force. So I think I'll go with the spring idea. So I will change the spring to a weaker spring, right? Or I can, I don't use the word weaker, I can use the word more flexible spring, but I think weaker is a better word. Why? Because earlier question they use the word stronger spring, right? So this is a language that SEAB understands, so we use weaker spring, so they can understand this word. If the spring is weaker, then it will not slow down the movement of this rod P. So then it can swing here with more kinetic energy and hit this. without changing the iron rod and plate arm, how can we change the setup to produce a louder tong sound? 2 marks. I need a louder tong. Tong sound is a sound when it hits the metal plate arm. Now I cannot change this. No changing. I cannot change the iron rod. I cannot change this. So how can I make sure this rod can swing and hit this harder? Now I need to go back. You see, go back and hit it harder. To go back and hit it harder, go back. Therefore, I will need this spring to be a really strong spring. So once I open the circuit and the electromagnet stops working, and there's no more magnetic force attracting the bottom end of the iron rod, the top end, then the iron rod will now swing back. And it swing really hard if this spring is a very strong spring. Then you'll hit this, top part will hit the plate very, very fast, and it will be a loud sound. So I need to suggest a change and explain. So first 1 mark, I suggest a change. So change the spring to a stronger spring. And this is 1 mark. So how does it work? When it's a stronger spring, so when will it start to work? When the switch is turned off, the stronger spring will exert a stronger pulling force on the iron rod. And what will happen when you exert a stronger force on an iron rod? It will swing it faster and make it hit R. R is the plate R. Make it hit R harder, producing a louder sound. Okay. Swing faster means more kinetic energy. More KE means there will be more sound energy. So in my answer here, my concept got to do with the idea of the spring. If the spring is a stronger spring, then there will be more elastic potential energy stored in the spring. If there's more elastic potential stored in the spring, they'll convert into more kinetic energy in the swinging iron rod, which will lead to more sound energy when the rod hits plate R. So this is the energy conversion that I have in mind when I answered this. Alright? Now, to make your answer clearer, you can even write this down for the examiners to see. More EPE in the spring, more KE in the rod, more sound energy, rod hits R. Make it very, very clear. Alright, I hope this helps you. All the best for your PSLE.